a very exciting topic, looking at our specific approach to AGI to be implemented in Hyperon, um, co-created but separate. So we'll dive into that a little bit in just a moment. We're joined today by Matt Eclay, our Chief Science Officer, Alexey Potapov, our Chief AGI Officer, and of course our own Ben Goertzel, CEO of SingularityNet. So we're so excited to be here today. Of course, we're just back from Istanbul, where we focused on platform roadmap topics, looking at the technical aspects of the platform going forward. But of course, we can't cover anything without building in Hyperon aspects. We covered DOS, meta on the platform, and of course Hyperon nodes and their integration with NewNet and Hypercycle, and how this all comes together to become truly decentralized AGI in the future, all these enabling technologies. So let's dive right in. Let's talk about what is Primus and what is that as distinct from Hyperon itself. Matt, Alexey, Ben.
Well, I would say that Hyperon, we already mentioned that there are two components which we are working on. One is a platform, a generic platform for AGI R&D, and one may refer to Hyperon as this platform. So we have different other cognitive architectures being ported to it, like NARS, non-axiomatic reasoning system, or Iris right now. So you can experiment with different approaches, with different architectures using this platform or framework. And another one is, of course, our own ideas of how to build AGI using this framework, and this is what is called Primus. So this is a difference.
Yeah, I mean, I think for folks who aren't deep into the tech, these labels probably seem to mean more than they do to me at any case. I mean, Hyperon is a new version of OpenCog, which is a real thing. But then, really, what matters is, you have a meta language interpreter. You have the atom space as a sort of meta representational structure. You have there's some atoms for you. Yeah, you have a distributed atom space, and I mean similarly, when we talk about like hypercycle, there's Toda IP, and then there's a hypercycle compute node, and then Primus, which we'll talk about a bit shortly, as a cognitive architecture and AGI design. I mean, there's a lot of different pieces in there. They cohere together, but they also each have their own importance. So, I mean, I think Hyperon is a collection of distinct interoperating things, and Primus is a collection of distinct interoperating things. But at the very high level, yeah, the way you guys have laid it out is correct. I mean, OpenCog Hyperon, sort of the descendant of the old OpenCog system, can be used to implement a variety of different narrow AI or AGI systems. It could be run on a number of different underlying frameworks. That could be run on AWS, or it could be run on a bunch of decentralized protocols like we're developing in SingularityNet. And then Hyperon could be used for a bunch of different things. And Patrick Hammer, Peter Isiev have been implementing some NARS, non-axiomatic reasoning system stuff in it. You could implement detailed biological brain simulations in it if you felt like it. And I mean, it's no one's doing that at the moment. So I mean, the history with the original OpenCog system was we also were developing it as a general platform for AGI and neural AI experimentation. and we had a specific cognitive architecture we were building on top of it. As it happened, nobody really used it for too much besides our particular cognitive architecture, or say Linus Vepstus's computational linguistics explorations. I think AI has advanced to a new stage now in terms of the amount of enthusiasm for building all sorts of AI systems. So I think that there's more chance of actually getting more users to jump on board and experiment with Hyperon anyway. And we've talked a bunch about the Hyperon architecture before, and a little bit less about the Primus cognitive architecture going on top of it, which itself is a huge topic, though, right? So let me see if I can share my screen here. Let's see how that works. Oh yeah, here. So here as a brief introduction to Primus. So this is actually a different Primus, but what we were previously calling the cognitive architecture, we're building on top of OpenCog. The old OpenCog was CogPrime, which was one of these very ugly names that I picked, assuming it would be replaced by something else better, and then that seemed not to happen for a long time. So finally, I decided it was time to pick another name. So this was my best stab at something in the general vicinity of CogPrime, but not too different. And we saw Elon Musk as a robot named Optimus, but if you're familiar with the Transformers, I mean, Optimus is just a big, scary robot. Primus is the ancient and ethereal, multiversal force for good existing across all multiple realities and alternate universes. So, I mean, we've not yet gotten quite to that level with our software version of Primus, but I guess we're, at least we've got our work cut out for us, right? So let me share something more meaningful here now. So
we'll get to Hyper Primus as well, so we'll get there.
Yeah, we may. So this lengthy paper on Hyperon that was posted on Archive some time last year actually covers a bunch of things that are properly in the domain of Primus as well as the Hyperon platform. So I'm gonna look at a little bit of this here just to frame the discussion, and then let me see if I can scroll down successfully. So there's another paper on Archive I published, I think 22, which was the general theory of general intelligence, which goes even more abstract and tries to go from sort of the general principles of how a mind works and sort of boil that all the way down to the level of how do we get a concrete cognitive architecture like this. So that was so if folks are not familiar with the whole way of thinking about AGI that I've been pursuing for a while and are curious, you can look at this one first. And there was a series of 10 YouTube videos where I sort of went through this long paper in some depth. I mean, what I did in this paper is try to start with some very general thinking about like what is intelligence, what is mind, what is consciousness, what is thinking, and from this very high level, try to boil down to, okay, how would you possibly implement a mind? And of course, there are many possible ways to do it. Now, the Hyperon infrastructure is certainly not the only platform one could use for mind implementation. And there's, as we said, a lot of things you can build on top of Hyperon. I think it's important to emphasize the distinction between software architecture and a cognitive architecture also. So this diagram here is not really a technical diagram, but it's sort of an impressionistic rendition of the software architecture underlying Hyperon. And to give a real software architecture diagram would just be more complicated with more different boxes and lines and look more confusing. But we can see the high-level software architecture here. You have a bunch of what are called spaces, including many that are based on meta, which is our language for representing typed metagraphs. And you can have other spaces embodying neural nets, hypervectors, and so forth. This collection of spaces can interact with external neural net frameworks. It can leverage various sorts of hardware. It interacts with a distributed M space. It stores a distributed metagraph across a network of machines, which has a cache. And I mean, then all this can run on centralized infrastructure, or it can run on decentralized infrastructure like Singularity Net, Hypercycle, and so forth. So all this sort of architecture is important. I mean, this is how we organize software processes on machines. When we talk about cognitive architecture, we're talking more about how does mental processing happen, right? And that's in a way living at the emergent level on top of the underlying software architecture. Now I'm scrolling down to the part of this long paper that dealt with what last year was called CogPrime and is now called Primus. And the detail of the Primus model, I'd say, is still largely given in the book Engineering General Intelligence from 2014. I mean, we've discovered a lot of new things since then and had a bunch of new ideas since then. But the high-level overview of the cognitive architecture is not really changed too much from what was said there. And I think with the Hyperon infrastructure, by the end of this year, as we scale it up further and further, we should finally have the infrastructure needed to experiment with, updated versions of these ideas at the the scale that they require, right? And the crux of this architecture is we have this weighted labeled metagraph, the atom space. Perception has to do with various sensors leading to the formation of different nodes and links in this atom space. Actions are represented by nodes and links that refer to, programs or other sorts of organized atomic actions, which are then translated into other representations for actuation, which could be neural spaces. It could be Rolang programs translated out of meta. But the crux of an action is represented as some nodes and links in the M space, which is then interpretable as some meta code, which then, as it runs, can trigger other software that is closer to physical actuators or network messages or whatever. Then beyond perceptions and actions, we have ambient cognitive activity. So you have just thinking processes going on all the time. So there's importance spreading, where activation and importance values, short and long-term importance, are spread along among nodes and links. Concept formation, where new concepts are formed by glomming together, grouping together, creating new nodes and links. reasoning, which builds new relationships from existing relationships. So this is all like spontaneous, self-organizing activity, not explicitly goal-driven. And then you have the goal-driven activity, which is also important, right? So that then you have system as a collection of top-level goals, and it's using reasoning and other methods to select and synthesize actions that it believes have high odds of achieving its goals, given its perception of the current context. And it's important that there is goal-driven activity. It's also important that not everything happening in the cognitive system is explicitly goal-driven activity. And I think at that high level, I mean, this is how the human mind works also. Like some of what we do is driven by goals, like basic ones from autonomic nervous system and others that we've learned. Much of what we do is not driven by any explicit goals. And we then have multiple cognitive processes represented in Hyperon by meta code embedded in the atom space, which combine to make all this cognitive processing happen. And when I said in the beginning of this session that Primus is a sort of grab bag of interoperating stuff, I mean, part of what I mean here is, we could add new things to the list of cognitive processes. We could remove things from the list of cognitive processes. You still have pretty much Primus architecture. I mean, each of these things is here for a reason. And in engineering general intelligence, we go over what each of them do and how they synergetically interoperate with each other. But there's a fair amount of wiggle room in the particulars of the architecture, which we can experiment with. And we can also instrument a system to automatically do this experimentation itself, right? So just to run through some of the AI methods here, each of which could use many hours of discussion on its own. So there's attention allocation that spreads attention and importance values among nodes and links in atom space. There's PLN, probabilistic logic network inference, which draws fuzzy and probabilistic conclusions from collections of observations or for knowledge obtained from natural language or ontologies and so on. But it takes knowledge in the atom space knowledge network and derives from other knowledge in the atom space knowledge network. Various methods of creating concepts like clustering, concept blending, and so forth. We use evolutionary learning like genetic programming and probabilistic variants in genetic programming to evolve new subnetworks of the atom space satisfying certain criteria. We can do probabilistic procedure and predicate synthesis, so use various probabilistic programming methods to synthesize new content based on the probability distributions implicit in the nodes and links in atom space. Pattern mining, so just identifying frequent or surprising patterns in the atom space and then embodying those as new content in the atom space. Goal refinement, so you have many goals with different sub-goals. You can learn new sub-goals of the existing goals. You can merge sub-goals together. Choose actions based on goals. I mean, you can also do more artificial life type stuff, like have rules embodied in the atom space where what they do is each rule modifies other rules to make yet other rules, which then resembles systems like replicode in the era cognitive architecture. So there's host of different cognitive processes. Let's see, was that the whole list? There's so many pictures in it.
It looks like one of the new things that I've noticed diving into Primus recently is our assignment of credit. I don't recall seeing that in some of the CogPrime descriptions.
It was
Is that
always there. You just didn't notice it.
okay?
Yeah. So, but I would say assignment of credit has a chapter in Engineering General Intelligence, Volume 2. So it was always there. The scheme I had for assignment of credit in Engineering General Intelligence, which was a sort of mix of a system of synthesized request for service objects working together with attention allocation, was never implemented beyond a very crappy prototype that I coded myself, and we never knew how well it would work. So I think it may be that we use a whole different method for assignment of credit in Primus now than what I envisioned in in Engineering General Intelligence Volume 2, although that approach might work also and has never really been tried out at scale. And that's an issue we have with a lot of these things is, these things seem to make sense conceptually, and you can implement toy models of them. The toy models do simple things okay until you've implemented them and played around with them at scale. Like, we can't tell how well they will actually work for yielding general intelligence. And I mean, that could sound like bullshit. You're like, well, we take something that works mediocrely, add a lot of scale, then it starts doing magic. Except, wait a minute, that's what happened with convolutional neural nets. Like, that's what happened with transformer neural nets yielding LLMs and so forth. Like, these networks also did some fairly interesting things at a small scale, but didn't set the world on fire. Then you split more data and more processing, and they start kicking ass, right? So, I mean, I think there's just a lot that we need to try once we get Hyperon scaled up a bit. Getting to the Hyperon alpha, as we've done recently, it's a big step in that direction. Between alpha and beta, a lot of what happens is increased scalability, increased usability, which will then let us try out all this stuff. So I want to very briefly flip through some of the images in this paper, because for people who are image oriented, that can be helpful. I mean, this is really just like human-like cognitive architecture, and not even that specific to Primus. But what we do in Primus, we take that sort of laundry list of reasoning, learning, concept formation, perception, action, cognitive methods. We take this list of algorithms and we use them to realize the functions in the boxes in these diagrams. And that's not the only way to try to realize the boxes in these diagrams. On the other hand, I think it's ideal to have fewer fundamental learning and reasoning algorithms and representational schemes than you have boxes in these sorts of cognitive diagrams. Because if each box in these diagrams has to have its own different knowledge representation scheme and its own different algorithm that a person has to come up with, the thing becomes very big and unwieldy. So what we try to do in Primus is have a relatively small set of representational schemes and learning and reasoning mechanisms, and then use them all to carry out a larger set of cognitive functions, as illustrated by the boxes in this and the subsequent diagrams I'm going to show. And of course, what has to happen there is these core learning, reasoning methods and representational methods have to sort of auto-specialize themselves to be able to deal with all these different aspects of what a human like mind needs to do. So here's the highest level diagram, which is not that original. It's very similar to what Paul Rosenblum and others have called the standard model of mind, and to some thoughts from cognitive scientist Aaron Sloman. I mean, you have perception, action, you have reinforcement, you have short and long-term memory, then you have motivation, action selection, you have deliberative and metacognitive processes happening in long-term memory, you have emotion and self. So this is sort of the high-level stuff we know a human-level mind needs to do. And you can then dig down into each part of it, right? So when you're talking about action and reinforcement, you're looking at different hierarchies for planning and inaction and reinforcement, which then connect with cognition and perception. When you look at language, you're looking at hierarchies of language comprehension and generation. Transformer neural nets are one ways to bake up this sort of hierarchy. There may be other interesting ways that we can experiment with in atom space in the coming couple years. Working memory was charted out quite well by Stan Franklin and his LIDA cognitive architecture, and there are different subsets of working memory dealing with sort of short-term procedural memory, short-term perception, short-term association, short-term episodic memory, and these all interoperate together in various ways. In terms of long-term memory, which is one of the primary functions conducted by the atom space, I mean, you need reasoning, you need learning of procedures, you need formation of concepts, telling of stories, modeling of the self, learning of new concepts, assignment of credit, learning of plans, simulating the world. All these things have to work together on the same collection of representations in long-term memory. Perception, again, you have perceptual hierarchies associated with different modalities, and these all need to cross-link together, as well as cross-linking with action and perception. Now, something I'm not going to go into now, but if you look at this paper, we tried to chart out for each cognitive method in Primus how it helps each other method in Primus. So we took like 16 of the cognitive methods, made a 16 by 16 matrix to try to lay out, how do each of these help each other, right? And I think that it's important thinking to do. It's also more than I'm gonna go through here, but I want to take a few minutes now, very aware that I've just given the abstract of Primus. I want to take a few minutes now to talk about how we work toward actually rolling this out, and then I'll turn it back to Alexei and Matt. So that this is just a preliminary set of notes that I made and bounced off some colleagues to look at sort of how do we develop Primus in practice. And first of all, I start looking at what are some use cases to use. And there's a bunch of interesting use cases in Singularity Net ecosystem already. We have small humanoid robots called the Mind Children, as well as the Hanson robots. We're doing a bunch of work on biomedical analytics. We're looking at twin protocol for controlling digital twins of people like myself and anyone else who signs up for twin protocol platform. Neoterics are to be little virtual agents running around and being sort of baby AGI minds in the Sophiaverse virtual world. Then we've also been experimenting with using logic systems and LLMs together to do scientific and mathematical question answering. So this is already a lot of different things, and it's going to evolve a bit in terms of which one becomes most important for testing out what Hyperon can do. But these use cases at least cover quite a lot of different bases. And then if we look at what sorts of development needs to be done, we could break it into a few different pieces, right? So there's what we can think of as developing the embodied agency core. So like a core autonomous embodied Primus agent, which is controlling an agent in a world, doing ambient and goal-driven learning and reasoning and attention allocation, trying to figure out how to be itself and get its stuff done and achieve its goals, and ambiently sort of interadapting with the world around it, right? And that doesn't even need to be that smart, that doesn't need to have the most sophisticated, scalable version of every learning algorithm, but it needs to have at least simple versions of all the different pieces of the architecture there. Then another important thing to do is, make reasoning and learning work together well at scale. Make PLN work with attention allocation, work with neural nets of various sorts, work with evolutionary program learning. And this is a bit more of a standard ML sort of thing, or ML meets machine reasoning, where you're trying to get algorithms to solve certain problems at a large scale. And then, of course, where the AGI magic is supposed to happen is where these things come together. Like, you don't get to AGI just by making reasoning and learning work together at large scale. You also don't get to AGI just by making an agent that has all the right pieces in its architecture. I mean, you need highly functional, large-scale learning and reasoning algorithms working within the right agent architecture, right? And then apart from that, there's a bunch of work in connecting Primus with external tools and with pulling in external development communities to help with Primus, which is certainly also highly important. And we're going through a process now of looking at these 5 target use cases and trying to flesh out what do each of these use cases mean for the development of each of the components. And without going into more detail than makes sense here, just to give you an indication of the kind of thinking that we're doing. I mean, we've gone through, made a list of all the different things that need to be done next, which include tasks connecting Primus to NARS, a bunch of things to make PLN work better, a bunch of things to make Moses evolutionary program learning work better, a bunch of things to make attention allocation work better, assignment of credit, goals and motivations, cognitive synergy, how to test and validate and encourage interoperation of the different cognitive algorithms, concept formation, perception, action, different kinds of memory, perceptual memory, episodic memory. So, I mean, for each of these aspects of Primus, there's a long list of tasks that we can look at. By the way, I'm joined here as well by the early version of our Mind Children robot. He obviously needs some work still, but we're working on the prototype of some sort of 3.5 foot tall robots to be like childlike companions to the Hanson robots, and they should be pretty reliable. They have like a charging station, like a Roomba or something, so they can buzz around learning using Hyperon all the time. I mean, I don't think robotics is necessarily the most important nor necessary part of working toward AGI, but it's certainly very, very interesting to give an AGI, proto AGI, that sort of view of the everyday human world, right? And now I think I've given a super high level overview. Now, one interesting thing I've been discussing with Alexei is to what extent can we have learning algorithms learn how to refine all these mechanisms to carry out all the functions needed for human level intelligence, and to what extent can we have general frameworks, like a very general learning or reasoning framework, where that general framework can do most of the heavy lifting, and it then sort of self-refines based on experience to do all the particular things. And given that Primus is a pretty broad architecture, there's various ways to do Primus, right? Like you could implement in ways that are more heavy on expert human implementation of different pieces. You could do it ways that are more heavy on guiding very abstract frameworks to specialize into the different pieces in the architecture. And that we're not exactly sure how that's gonna flesh out, but it may be interesting to have Alexei and Matt enlarge in that direction, or anything else that they are inspired to.
I was interested in kind of circling back to something you said earlier about the analogy with deep neural networks, CNNs and transformers in particular, in terms of their scaling properties. They didn't scale until we had the finer power and the architectures.
I mean, the thing is our mathematics sucks, right? So this is one thing that becomes clear after you dug into the math of AGI a while, is that finding algorithms that will yield massively powerful AGI when you give them a lot of computers is not as hard as one might think at first. Like making nice, simple, elegant AGI algorithms that will be as smart as you want when you jack up the amount of data and compute you give him, is kind of easy once you understand the math of AGI a bit. So then on the other hand, exactly how fast an AGI capable algorithm gains capability as you scale up its resources is largely voodoo at this point. And I mean, we don't have strong mathematical theories to tell us. I mean, like for transformers, if you train a transformer model on 100 trillion parameters, what happens? Or for a genetic algorithm, we have an infinite population size theory, but what happens when the population size is 1 billion versus 1 million for a given objective function? There's some theory about that, but it's not that good, and it often doesn't tell you what you really want to know. So there's still, even with all the math theory, there's just a lot of trial and error experimentation that will be needed. I mean, unless we wait for some really huge theoretical breakthroughs, which it seems currently may come more slowly than the trial and error gets done.
Oh, I was going to point out that part of the impetus for the new Hyperon system versus classic OpenCog we were beginning to see some interesting emergent phenomena in classic OpenCog.
Sure, like in work,
I would say, but now we've got with Hyperon a much cleaner, more flexible.
With PLN and ECAN together, we were getting some interesting.
Exactly.
Yeah, true.
And so that was the analogy I was trying to bring to what happened with CNNs and transformers. With the Hyperon architecture, we are now beginning to have the capabilities to really take our architectures to the next level.
Yeah, I would like to make a comment on this issue of the part of engineered and the part of emergent or learned behavior. So indeed, what transformers show is that even with quite simple architectures, a lot can be learned, and this yields great results, at least practical results, and they're also instructive in terms of AGI. In the field of artificial general intelligence, there were also some very simplistic but deep models like universal induction and IXC, which would be super intelligence provided an infinite amount of resources, and they were always criticized for being not efficient. And indeed, it's clear that they will not scale up because resources are always limited, but there are different theories of self-improvement, like Gödel machine by Schmidt-Huber and others. And we actually don't know what should be the optimal compromise between what is engineered, what is hand-coded, and what is learned by putting more and more computational resources. So if it's not just a fixed inference engine, but something which is self-improving, then maybe putting more computational resources will be more efficient than hand-coding everything. And the whole history of machine learning and actually of artificial intelligence in total is the history of automation of the work of the AI researchers themselves. So initially, all the heuristics were hand-coded. Everything was created from scratch. Then expert systems appeared with some reusable components, and then machine learning started to yield useful results, and so on and so forth. So it is absolutely clear that we need a right architecture in order for it to evolve to a full-fledged AGI. It's not just putting computational resources for anything. And if you just have a very, very huge transformer, it will not scale up to AGI like universal induction or AXI, but for different reasons. But still, it's really an interesting question to go back and see how the ideas behind cognitive architectures, which were put forward when more things were hand-coded, could be optimized right now, but by not crowdsourcing them, for example, or some other ideas like creating an AGI in a style of Linux, when an open source community can compete with large companies. So these ideas are still valid, but personally, I have a feeling that we need to put more resources in self-improvement and self-learning of the baby or proto-AGI systems. And a good side is that Primus cognitive architecture also contains all these components like genetic programming, algorithmic chemistry, and so on. But it also contains many other components, and the question for us is to how to spend our resources. And as AGI is the capability of solving a variety of problems and achieving a variety of goals in a wide range in environment, given the limited amount of resources, it's the same here. So it's the question of the optimal route towards AGI given our limited resources.
I'm very interested in what Ben was pointing out, building a general learning system for Hyperon, for CogPrime, for AGI. Alexei, does this to you look something like or related to machine learning type techniques, or something fundamentally different?
Well, machine learning is a very wide field, and it encompasses not only neural networks and deep learning, but you can put genetic algorithms there, as well as universal induction. So it depends on how we define terms.
Yeah, I mean, there's a lot of cases where the same basic math and in some sense the same learning approach can be used in a narrow way or in a more general intelligence oriented way. I mean, automated program learning is one example. I mean, if you can use genetic programming to learn a sorting algorithm or find patterns in biology data, or you can use it to learn a cognitive control schema for a proto-AGI system. And I mean, for logical reasoning systems, I mean, you can use a logic engine to do math theorem proving, and you can use ML to tune the theorem prover. But then you could also use similar logical theorem proving approach to do AGI-ish common sense reasoning. I think when you dig into the details, the way that you're using these algorithms often comes out different for AGI or more standard applied narrow AI use cases. So as an example, with evolutionary learning, very often in an AGI-ish context, the fitness evaluation is very expensive. So you're evolving a bunch of different things, but often in an AGI-oriented context, to evaluate whether one of the things in your population is good or not, you're doing something involving the rest of a cognitive system, which takes non-trivial compute time or even feedback from the external world. Whereas in machine learning applications of evolutionary learning, often, not always, you've packaged up some simple fitness function that can quickly be evaluated. And in a logical reasoning context, we found most of the theorem provers that are useful for doing logical reasoning in a math context don't work for reasoning in a common sense, everyday context, even though the reasoning is very simple relative to math, because in common sense reasoning, you have a large number of premises. You just have a large amount of information you need to take into account in doing reasoning, whereas in math, you tend to have a small number of axioms in your axiom system. And just for practical reasons, the theorem provers used for math were tuned to deal with a small number of premises, not a huge amount, right? So what I find so far is a lot of the same basic learning or reasoning algorithms or representation techniques can be used for narrow things or as pieces of an AGI architecture. But when you dig into the details, the ways in which you're using them are quite different in a way that makes a difference for the implementation and the scaling properties. So the devils are often in the details. Defies running through in this sort of brief hour-long context.
Yes, definitely. Thank you very much, Alexei. Thank you, Ben. All too brief, definitely. I'd love to touch on just for a minute, if we can, people who are interested in learning more. You've pointed at papers, developers who are interested in getting involved and learning more. What are some of the resources? What are some of the ways to get involved within Hyperon, within Primus, and contribute?
Yeah, I mean, OpenCog Hyperon is open source project, and there's a code online. You can look in, for example, the true AGI-IO repository. There's Hyperon experimental version, which is Hyperon Alpha, and there's a bunch of meta language tutorials which Alexei and his team have put online that Haley you can share the link to. And I mean, these are more about how to do implementation of simple things in the Hyperon Alpha using the meta language, but I mean they're a way to get a start, right? So that's the nitty-gritty bit of getting started with implementing stuff in Hyperon framework. And then for the conceptual aspect of what it is to be implemented, I mean, the papers that I showed briefly earlier here, the overview of Hyperon and then general theory of general intelligence. I mean, these, and then the original book, Engineering General Intelligence, volumes 1 and 2. I mean, this is a lot of information, which is heterogeneous in nature and is a time consuming to absorb. But I mean, that's sort of what's there regarding the Primus cognitive architecture. And I mean, I won't apologize too much regarding it being a large amount of information, because I mean, we're trying to build an AGI. Like I think it's that there's an expectation from working with CNNs and transformer neural nets. So like you could come up with one pretty simple neural architecture, and then this is going to give you a thinking machine. I mean, I don't think it's going to be quite that simple as like, tweak the attention mechanism in the transformer, cross-link it to another net during reinforcement learning, and you got an AGI. Like, I mean, honestly, the Primus architecture and the Hyperon framework together are vastly simpler than what you see in a textbook of neuroscience. right? So, I mean, we're still abstracting things and making them simple and elegant compared to the human brain, such as we believe it operates. But it is a more complex thing than any one of the currently, fashionable commercial neural net architectures. And how much we can simplify it remains to be seen. On the other hand, our routes to simplifying it seems to involve abstracting things more and more, which don't necessarily make them easier to digest either. It means there's more abstract tooling to master, right? We're working on a list of Hyperon and Primus related projects to put out there to the open source development community, but associated with SingularityNet's deep funding program, so that we can pay people in AGIX, will soon to be ASI tokens. We can pay people in ASI tokens for doing open source R&D or application-based development along the lines of the Primus architecture on the Hyperon infrastructure. And there will also be grants for people doing stuff they invented themselves on Hyperon or in the spirit of Primus. But we're working on a specific list of projects that we think are sort of low-hanging fruit to do right now. And I'd say as more and more people take up these projects, then there will be more and more open source code projects building in OpenCog, Hyperon, and Primus, needing people to just plunge in and fix things and make patches and so forth. So I'd say with the Hyperon Alpha, it's just getting started, but during the next months and the rest of this year, I mean, I think we're going to see a bigger and bigger flourishing community of researchers and developers plunging in. I mean, we've been waiting a while to get to this point, right? Because I mean, the threshold of the alpha, I mean, it really is an alpha. Like, it's not scaled up yet. There will be breaking changes, but it is a system that I feel comfortable inviting AGI enthusiasts to plunge into and start helping us build. Not yet at the point where the random AI application developer can necessarily plunge in and start doing things as easily as you can, like, script Python to use Llama 3 or LangChain or something. I mean, we still have a few development cycles to get to that level of ease of use. But I mean, if you plunge into the meta tutorials, you'll start to get a feel for it.
Absolutely. Thank you very, very much. That was excellent. Lots of opportunities coming forward for participation, for learning, for preparation to get involved, and that's just going to grow. We've seen already just the kind of the growth and the attraction of really high caliber, amazing researchers to the project over the past years. I've seen that just grow, and it seems to be accelerating in general into the core team as well as generally. So we're going to sign off. Thank you very much, Matt. Thank you very much, Ben. Thanks very much, Alexei, for this great dive into Primus. Not enough can be said in an hour, but it was a great overview. Thank you very much. Yes, and our introduction to the Mind Children, who will possibly come with their own Ben Goertzel hat as the added bonus future Neuralink component, right? Everybody, please sign up register for the AGI conference coming up August 13th through 16th. Registration
Another way to
now.
get involved.
Another way to get involved. Yeah, absolutely. Attend live or attend virtually and see the amazing research that's going into these deep, well thought out, complex but really necessary cognitive and AI architectures to actually achieve AGI, general intelligence. So that's agi-conf.org / 2024. We'll put the link in the channel as well. And again, you can now register for that. So thank you very much all, and we'll see you next time.